Alright everyone, it's Mr. Rudy back with yet another video. So today guys is going to be our first subsection in Unit 6, which is on endo and exothermic processes. Guys, we're starting a new unit on thermal chemistry today. So thermal chemistry is the study of the relationship between chemistry and energy. Okay, so it's in the name there. You'll notice that I gave I want to start off by talking about an example of the chemical reaction that's in hand warmers. So the oxidation of iron, right, is going to form iron 3 oxide, but something that we haven't necessarily seen it in a chemical reaction is that it's also releasing heat, okay? So moving forward, everybody, we're going to start talking about, in this unit in particularly, okay, is energy being absorbed or released by a chemical reaction? And in the energy in this case specifically, we're going to be focusing on, in this chapter at the very least, heat energy, okay? So what is energy? Energy is the capacity to do work, okay? Work then is the result of a force acting upon a distance, okay? As an example, pushing a box across the floor, that is work. And then heat, or Q, is the flow of energy caused by the temperature difference. So guys, I want to briefly just draw something that will hopefully make this a little bit more meaningful, right? So imagine I had a pool table with billiard balls, right? So here's my billiard ball. It's in motion, right? Because I am drawing an arrow telling you it's in motion. Okay, so this would be kinetic energy, the motion of my billiard ball. Okay, now if my billiard ball collides with another billiard ball, so we'll say it's this red one here, this red one, once the collision itself would be the work, right? So the collision itself would be the work because the energy of the blue billiard ball is being transferred to that of the red billiard ball. And then the red billiard ball is going to now pick up the energy that the blue billiard ball had. Okay. So that is a way that we can think about the difference between energy and work. So again, imagine you're playing pool. Okay. When you first, when the billiard balls are in motion, that's the kinetic energy. Now, once the billiard balls collide with another one, right, that collision is the work because the work is transferring the energy. Okay, so that's the force acting through some distance. So once that energy is transferred, that's our work. And then once the billiard ball starts to move again, that is then converted into kinetic energy. Okay, so when it comes to energy and work, keep it simple. Think about pool tables, okay? Now, as far as types of energy that we're going to talk about in here, we'll start off with kinetic energy, which is the energy of motion. Again, this was the energy of my billiard balls moving back and forth, okay? In chemistry, we're specifically studying the motion of our particles. Potential energy is associated with the position or composition of an object. Guys, we typically think with potential energy in terms of gravitational potential energy. So again, just take the pencil you have right now that you're writing these notes with and lift it up a couple feet. You've now given that your pencil gravitational potential energy. Now, if you let your pencil fall, right, it will then be converted into kinetic energy. Okay, the energy of motion. Thermal energy is the energy associated with the temperature of an object. And then finally, chemical energy is the energy associated with the relative positions of electrons and nuclei in atoms and molecules, also a form of potential energy. Guys, that's a very fancy way of saying for chemical energy, it's the energy that's stored in a chemical bond. So that's just a very fancy way of putting it. Okay. So the first law of thermodynamics is the law of conservation of matter, which states energy can be created nor destroyed. It can only be changed. Okay. So energy can be transferred from one object to another and can assume different forms. So guys, these two diagrams here really illustrate this point well. So energy or light energy from the sun is absorbed by plants through a process known as photosynthesis. The photosynthesis takes in that energy and converts it into sugar. Animals that eat plants, us included, will take that energy that's stored into sugar, that chemical energy. We break that energy apart using, the Krebs cycle and glycolysis, okay, to form mechanical energy. So we're taking the energy that's stored in those sugar molecules, we convert it to mechanical energy through the Krebs cycle and glycolysis. Now, we could also take something that's a bit more mainstream here in terms of like, oh, what's happening in a power plant? Well, there's chemical energy stored in coal or gas. When that's heated, that energy is transferred into heat energy. The heat energy is then transferred into kinetic energy to spin those turbines. As those turbines are spinning, it will be transferred into electrical energy using a generator and a transformer. And finally, that electrical energy is the same energy that is that powers the lights in our house or our classroom, wherever we're at. Now, again, none of that energy was created nor destroyed in that process, guys. It was only changed. So another way that you might see the first law of thermodynamics rewritten is the energy in the universe is constant. Okay. Again, that simply means we're not creating energy, we're not destroying energy, we can only change it. All right, how do chemists study matter? Well, we will look at the system, which is the portion of the universe that we want to study. The surroundings is everything else in the universe, and then the universe is the system and the surroundings. Now, guys, in this unit in particular, we're really going to start talking about the system and the surroundings because we're going to be seeing where the energy, or in our case, in heat in most cases in this unit, where is it traveling from? Is it going into the system, what we're trying to look at studying? For us, the system could be the chemical reaction. It could be the physical change. It could be a phase change. It could be, you know, simply a substance like the gallium metal in this picture here, okay? Surroundings is just everything else then, okay? So the system, okay, if it's endothermic, energy is going into the system. And if it's exothermic, energy is leaving the system and going to the surroundings, okay? So in this case here, we have gallium metal, which is our system. The hand is the surroundings, and the gallium metal is melting, right? So that means energy went into the gallium metal to cause it to melt, okay? All right, now if we're looking at the beaker and the solution, right? So the beaker and the solution is the system itself. Okay, so that's the heat exchange that's being involved here. And then the surroundings would be the table and the air. Okay, now typically, guys, as we'll learn in a future unit, heat will travel from a hotter substance to a colder one. So if the beaker is hotter, if the beaker and the solution are hotter than the surroundings, then heat's going to go from the beaker to the table and the air, and vice versa would be true if the air and table were hotter. Okay. Now, enthalpy, guys, is the sum of internal energy and the product of pressure and volume. So H is equal to E plus PV, where H is enthalpy, P is the pressure, and V is the volume. The change in enthalpy is equal to the change in energy plus the pressure times the change in volume. Guys, I'll be upfront and honest with you. In a lot of cases, when we're talking about delta H equals delta E plus P times delta V, this is really for a future chemistry class that if you continue to take chemistry that you'll certainly talk about. We're more interested in terms of the enthalpy change of the system is equal to the energy flow as heat. So we're really concerned with this second bullet here, specifically what's highlighted in blue, because many of the problems that we're going to be referring to is at a constant pressure. Okay, so for a chemical reaction, delta H is the enthalpy of the products minus the enthalpy of the reactants. Signs of delta H: if it's positive, you have an endothermic process. If it's negative, you have an exothermic process. Pretty simple there. Endothermic processes is when energy flows into the system from the surroundings. Phase changes that are endothermic include melting, vaporization, and sublimation. Here, bonds are being broken. Chemical reactions can be endothermic. So, an endothermic reaction is when heat is absorbed from its surroundings. Products have more energy than the reactants. Okay, so if you take a look here, my reactants have lower energy than the products because the energy is being absorbed. And then here's a nice diagram here showing you that heat is traveling from the surroundings into the system. That's an endothermic process. Vice versa, we have an exothermic process, which is when energy flows out of the system and into the surroundings. Phase changes that are exothermic include freezing, condensation, and deposition. Bonds here are being formed. Chemical reactions can be exothermic. So, exothermic reactions is when heat is released or emitted to the surroundings. The energy of the products is less than the reactants. So, here's an example reaction. But if you guys take a look here, the reactants are starting at higher energy than the products are. That's because energy is being released there. Okay, so exothermic, the energy is traveling from the system to the surroundings. Okay, guys? Here are heating curves, a brief introduction because we are going to revisit these in quite a bit more detail in the future. Okay. But if you guys take a look here, you'll notice that for an endothermic process, I have to add heat to my system. Okay, so I'm adding heat to this particular system. Where if I'm in an exothermic process, so I'm trying to take the gas and condense it back to a solid, I will be removing heat from said system. Okay, making solutions. So making solutions are both endo and exothermic processes, guys. In order to break the solute-solute interactions, energy has to be absorbed. So that would be exothermic. I'm sorry, that's endothermic. If we need to break the solvent interactions, energy is absorbed again, also endothermic. However, when the solute and the solvent interactions begin, they will release energy, so that's exothermic. So, really important, guys, on this slide is breaking bonds or intermolecular forces requires energy, while forming new bonds or new intermolecular forces will release energy. And guys, that's exactly what this diagram is illustrating here. So again, I have to put energy in here to break my solvent-solvent and solute-solute interactions. Once my particles are separated, they are then free to interact with each other. And when a new intermolecular force or chemical bond is formed, a release of energy occurs. So in this case, a lot of energy is released. So my delta H of solution, or my net energy from the beginning to the end of this process, is exothermic, meaning that a bunch of energy is being released. Okay. Presumably, guys, my solute here was a salt, so I had to break that ionic bond in order to dissolve it. The solute is likely water, so I had to break the hydrogen bonding or the intermolecular force there. And once the ions and the water molecules were separated, they probably formed a new intermolecular force, ion dipole, which released a lot of energy, resulting with a net delta H being less than 1, which simply means the process is exothermic. Okay, example problems I do. So, guys, what we're looking for here is we want to determine if the process is endo or exothermic, and then identify the sign of delta H. Well, sweat evaporating from skin is endothermic, right? Energy is required to go from the liquid state from the liquid state to the gaseous state. So we would have a positive delta H, so because it's endo. Water freezing in a freezer. This would be exothermic, everybody, because energy has to be released in order for liquid water to form a solid. So that would be a negative delta H. And then wood burning in a fire would be exothermic because heat is being released to the surroundings. So delta H here would be negative. Now, real quick, although they didn't ask us to do this, letter A is a physical process. Letter B is also a physical process, but letter C would be a chemical process. Okay, let's continue on. So it says a solution of ammonium nitrate was created by dissolving 5.02 grams of ammonium nitrate in 100.0 milliliters of water at 22.3 degrees Celsius. After forming the solution, the temperature was 17.3 degrees Celsius. The questions are, did heat enter the system or leave the system? What is the sign of Q? And then, was the dissolution process endo or exothermic? Guys, keep in mind that Q is heat. Okay. And again, if we had a positive Q, that's corresponding to an endothermic process. If we had a negative Q, it is corresponding to an exothermic process. All right, guys, I want you to pause the video and try this one on your own. All right, guys, and hopefully you said that heat entered the system, so Q is positive, and that the process was endothermic. Now, guys, keep in mind here that the water itself was the surroundings, and the water had a change in temperature from 22.3 degrees Celsius to 17.3 degrees Celsius. Well, that means heat went into the system. So if heat went into the system because it appears that we lost energy, right? That the water decreased in temperature. So that means that energy went into the system, therefore it's endothermic. With that being said, guys, that's the end of today's video. If you have any questions, let me know.